Okay, so this is the review session for EGME 410, midterm 1 for spring 2021. All right, and so I checked the poll on Canvas, and these were the topics that were most requested. So number 1 was beam equations. Very close behind that was truss equations, and then a distant third was direct stiffness and springs. And so what I generally expect is that probably for this review session, I'll focus just on beams and trusses. And then maybe for like 5 minutes at the end, we'll review springs and direct stiffness. Okay, and so the plan for this review session is I'm going to go quickly over kind of the conceptual information and the theory that you would need for for both of these, and then I'm going to do some examples from the homeworks. And so I know we've done kind of the in-class examples before, but let me kind of work through some of the homework problems that are associated with these. And I'll do it in the style of the questions that I would ask you on the exam, just so that you kind of get a trial look at what kinds of things I expect you to do. Okay. And so with that, let's go underway. And so let's start with beam equations or beam elements. All right. And so beam equations and beam elements have to do with structural elements that have transverse displacements and rotations. And so we have basically two modes of deformation here. Okay, and so if we show kind of a typical beam element that looks like this. Okay, and so everything that we're going to be considering in this first midterm are kind of long, slender, structural elements. A beam is going to have the following deformations. Right? And so a transverse displacement is just any kind of deformation that's perpendicular to the axis of the element. Okay, and so if the element goes left and right, transverse displacement is going to go up and down. Right? And we usually label this, accordingly. Right? And so usually we call the left node, we call that node 1. The right node we call node 2. And so the transverse displacement node 1, we call it U1Y. And then in addition to this, of course, we have rotations as well. Okay? And so rotations, you can kind of almost think of them as like changes in orientation or changes in slope at the two nodes in the element. Okay? And so we usually denote those theta 1 and theta 2. Okay. And so this is in contrast to truss elements. If you remember from truss elements, what we assume for those that they only displace transversely, or not transverse, axially, and so they only displace in tension and compression. So beam elements kind of cover everything else that you can do. Okay. And what causes these transverse rotations and these transverse displacements and rotations are going to be transverse forces and moments. Okay? And so the kinds of forces that we're going to be looking at, for these kind of beam elements look like the following. Okay? And so they're always going to be forces that are perpendicular to the element. Okay? Okay. And so here we're going to have F1y. This is F2y. Okay. And there's also going to be rotations. And so we have, or moments, sorry. So we have an M1 and 2. Okay. And so remember, whenever we're doing finite element problems, we're always forming a relationship between, what are the external effects, what are the external loads, and the resulting displacements. Okay. And so, what I've shown here, that in this lower part right here, this is the, all the external loads or external forces. Then up here, what we have are the resulting displacements. So this is almost like, you can almost think of it as the structural response. And so anytime we do a finite element calculation, whether it be in ANSYS or with hand calculations, we always want to find the relationship in between these two guys. Okay. And the way that we form that relationship, at least mathematically, is through the element stiffness matrix. Okay. Because you know, basically what we're going to have is a linear transformation in between, you know, the forces and the resulting displacements. Okay. And so let me write down what the element stiffness matrix is for a beam. Okay. All right. So the element stiffness matrix looks like the following. And so you can find this in the lecture notes. But basically, what we have here is, you know, all of our external forces, right? Okay. And so that's a list of all of our external forces. So we have the transverse forces on each of the nodes and also the moments. Okay. Okay. Then we have EI over L cubed. Okay. And I'll define what those are in a second. And then we have this 4x4 matrix here, which is going to relate it to the displacements. Okay. So we start with 12, 6L minus 12, 6L. Okay. 6L, 4L squared, minus 6L, 2L squared. Okay. And then we have minus 12, minus 6L, 12, minus 6L, and then 6L, 2L squared, minus 6L, and 4L. Okay. And of course, these are going to be multiplying by the vector of the nodal displacements and rotations. Okay. So we have U1y, theta 1, U2y, theta 2. Okay. Right. And so let's define all of these properties here. Okay. And so first we have E, where E here is our Young's modulus. Okay, so remember the Young's modulus is basically a description for how strong your material is, essentially. And so it's kind of our property of structural strength. I here is the moment of inertia. Okay. And L, which is the last quantity that we have here, is the length of the element. Okay. And so, you know, in order to form your element stiffness matrices, you basically need to plug in to, you know, this expression here. So it's a lot of plugging, I know, but you know, it is just kind of just a lot of just straightforward plugging and chugging. And remember, you know, when you're plugging in this many numbers into, you know, into this equation right here, it can be really easy to kind of lose track and kind of, you know, maybe make a mistake here and there. And so remember always your sanity checks for, you know, for your element stiffness matrices. Okay? And so the first one that I always do is I check to see, so I draw a line on my element stiffness matrix like that, and I check to see if my matrix is symmetrical across that line. And so what you should see is that, you know, you have equal values, you know, in this and these two slots, right? You should have the same values in these two slots. Okay. And I know it's obvious, but kind of when I'm circling it from this equation right here, but after you plug in your numbers, you know, you should still see that those two values are equal. So that's the main mistakes here that I see, you know, a lot of people make, is kind of, you know, making mistakes with the symmetry. And you know, kind of the nice thing about the element stiffness matrix is that there's kind of built-in redundancy, so you can use that to kind of check your work. Okay. All right. And so that's the element stiffness matrix. And so remember, whenever we're doing a finite element problem, we always start with this. We always basically plug into this guy and then you know, use that to solve the rest of the problem. Okay? And so you know, before I kind of move forward, you know, I do want to kind of address something else too, because this is kind of a question I got on the most recent homework too. Right? And so, you know, the question I got on the most recent homework is, you know, how do I know which element stiffness matrix to use? So should I use the one for the beam, And should I use the one for the truss? Okay. Um, and so, because visually, these beams and trusses, they look the same. So they just kind of look like just long, slender elements. And so, the question is, how do we know which one to use? And so, there's some subtle things that you can check just to see, like if the problem involves, if it has a moment. If it has a moment, then it has to be the beam equations, because there's no way for a truss element to support a moment, right? You can also check the loading, and so if you have a loading that's perfectly transverse to a beam, that's also an indicator. But I think the easiest way to check is just to kind of read the problem, and the problem will tell you what types of elements that you have that you're going to be working with. And almost always, it's going to tell you probably in the very first sentence of the problem. So the very first sentence of the problem will usually be, consider this assembly of truss elements, or let's consider this assembly of beam elements, okay? And so we haven't done any problems where we've kind of mixed and matched. And so, we haven't done a problem with both truss and beam elements. And there's not going to be anything like that on the exam, so don't worry about it, okay? And so it's either going to be one or the other, right? And so kind of just read kind of the first sentence of the problem, and it'll tell you which type of element that you want to use. All right, and so before we launch into an example problem, let me first let me talk a little bit about the types of supports and the types of constraints that we can use. Okay? Probably you guys know this already, but I'm just going to review it just for the sake of completeness. Okay. All right, so we have three types of supports that we can do. Okay, and so the first type of support is a fixed support. Right, and so for the fixed support, visually it usually looks something like this. Like it looks like our structural element is kind of welded into the wall. And what's unique about this support is that it constrains all the degrees of freedom that are possible, at that node. Okay, so we call this node 1 right here. What this is going to do is it's going to constrain all degrees of freedom at the supported node. Okay. Right. Because at any node like this, we have, if we consider kind of the general case of, we have both trusses and beams, we have three possible degrees of freedom here. So we have the displacement in the x direction, we have the displacement in the y direction, and we also have theta, which is the rotation. Okay. And so in a fixed support, all of these guys are going to be set to 0 because they're, that's what the fixed support does. And so anytime you have a fixed support, you can just basically just knock out every single degree of freedom there. Okay. And so kind of one level down from this is going to be the pin support. Okay. And so visually it looks something like this. Okay. So we have our element like that, and we have a little triangle here, and then we have that triangle there can be fixed to the ground. And so the pin support, what this is going to do is it's going to constrain all displacements but leave the rotation free. And so this is going to be, so we'll have ux is going to be equal to 0 here, uy is going to be equal to 0, but theta here is going to be free. Okay. And what it means for a degree of freedom to be free is that, you know, we're not going to knock that out in our global linear system, right? Because typically what we do is that, you know, when we apply these constraints, we kind of knock out that entire row in the global linear system. And so, you know, we change, you know, whatever was there before, you know, we kind of don't really care. We make everything 0, and then we put a 1 on the diagonal. That's what we normally do when, you know, when the thing is constrained. But when a degree of freedom is free like this, what we do is we just leave it alone. And so, you know, we don't have to do anything there. Okay, so that's the first two types of support. So we have a fixed support and a pin. And the last type of support that we have is a roller support. And so a roller support looks like this. And so it usually is a triangle with little wheels on the bottom. Okay. And then those wheels might be resting on something there. Okay. All right, so the roller support, you know, is kind of one level down from this. And so from here, you know, it's going to allow rotation, and it's going to allow, you know, displacement in the direction of the roller. And so basically, you know, we're going to have displacement going in this direction right here. Okay. All right. And so what this means, since here the roller is in the x direction, we're going to say ux is going to be free. Okay. Uy here, which is, you know, the direction perpendicular to the roller, that's going to be constrained. So we'll set that equal to 0. And then, of course, you know, rotations are going to be free here. Okay? So the roller supports are kind of the least constraining support that you can do, you know, in terms of that. Okay. Okay. And so, you know, when you're doing your finite element problems involving beams or trusses, you know, you definitely have to look at the types of supports that are used and make the appropriate adjustment to the stiffness matrix. Okay? Okay, and so with that, let's jump into an example, right? And so let's do an example from the homework. Let me go ahead and pull that up. Okay, and so this is going to be problem 3A on the homework. And so I'm not going to do it all to completion, you know, because that homework is still out there right now. But I'll at least show you how to set this up, you know, and do the work that I would expect you to do on the midterm exam. Okay, so this is going to be problem 3A from homework 2. Okay, and so here what we have is we have a beam. Okay, and the beam has a fixed support here on the left side. Okay, and then what we have are 3 beam elements. And then we have a spring that's being that's holding it up on this side, right? And so let me label all of the elements here, right? And so we have elements A, B, C, and D. We have node 1 here on the left-hand side. We have node 2 here in between there, node 3 here, node 4, and also node 5. Node 5 is just a fix, so you know we actually don't really need it, but you know, just for the sake of completeness, let me go ahead and label that. Okay. All right, and so what this problem says is that all the beams here are identical, and so their properties are given by the following. So the length of all the beams is going to be 3 meters. Okay. The Young's modulus we'll say is 50 gigapascals. The moment of inertia here will be 9. Actually, really big. Right, 9 meters to the fourth, right? And then KD, which is the spring constant for this spring, we'll say it's 175 meganewtons per meter. Okay. All right. And so let me do this problem here. According to how we do this in the we have a vertical load. I always forget the load. As we have a vertical load of P, and this P is 350 kilonewtons. Okay. And so let's go ahead and do this problem according to if I assign this on the midterm. So this problem is a little bit too complex for the midterm just because it's it's 4 elements here. And what I promised you guys with that on the midterm, there's only going to be maximum of 2 elements. But by doing this, you'll get a sense of how to actually set these up in the midterm. Okay. All right. So step 1 is going to be compute the element stiffness matrices for all the elements involved. Okay. And actually, for this step, because our 3 beams here are identical, we can kind of basically use the same element stiffness for that. All right, and so since all of these guys are beam elements, we're going to use the element stiffness matrix for a beam. So let me start with Ka, and so Ka, this is going to be EI over L cubed, which we can go ahead and compute just now, just because we have all those numbers, okay? And so this is going to be, our Young's modulus is 50 gigapascals, right? And so we're going to plug in 50 E9 pascals, right? And so when you're plugging in for these, material constants out in front, usually it's better to kind of, or it's good to convert all of these guys into a standard system of units, just that you're kind of multiplying apples and oranges, right? All right, and so the Young's modulus are that's the Young's modulus. Next, we have the moment of inertia, which is 9 meters to the fourth, okay? And then we're going to divide that by L cubed. And so L cubed here is, let's see, L here was 3, right? And so we have 3 cubed, which is 27, okay? Right, and so if we compute this out, then what we get is 50 E9 times 9 divided by 27. And so what we get from here is 1.67 times 10 to the 10th, newtons per meter. Okay. All right. And so that's that guy. Okay. And so now that we have this value out in front, what we can do is we can just then plug in for all the other values in the element stiffness matrix. Okay. So this will be 1.67 E10. Okay. And then we're going to multiply this by everything else that we all the other values in the element stiffness matrix. So let me go ahead and pull it up. Okay. And so this is going to be 12. 12, okay? And then we have 6 times L. And so 6 times L here is 6 times 3, which is going to be 18. Okay. Then we have a minus 12. Then we have a 6 times L, which is going to be 18 as well. Okay. And so that's the first column of our element stiffness matrix. Next, we have 6L, and so we have 18 here. Then we have a 4L squared. And so we have 4 times 3 times 3, which is 4 times 9, which is 36. Okay. Then we have a minus 6L, and so we have a minus 18 here. And we have a 2L squared here, which is going to be 2 times 3 times 3, which is 18. Then we have a minus 12. Then we have minus 6L, and so that's going to be a minus 18. Then we have a 12. Then we have a minus 6L, so that's minus 6 times 3, which is minus 18. Okay. And we have 6 times L, and so that's going to be 18. And then 2 L squared, and so that's going to be 32 times 2 times 9, which is 18 as well. Okay. Then we have minus 6L, so that's going to be minus 18. And we have 4L squared, which is going to be 36. Okay. Right. And so that's the element stiffness matrix for A. And then so from here, we're going to multiply by the degrees of freedom that A is, the element A controls. Okay. So this element A is going to be on nodes 1 and 2. Here we're going to list out all the degrees of freedom for nodes 1 and 2, right? So we have U1y, theta 1, U2y, theta 2, okay? All right, and so that's Ka. Kb. So Kb is going to have the exact same numerical values as Ka, but they're just going to work on different nodes, right? And so let me just kind of repeat everything here, okay? And so you have 1.67 times 12, 18, minus 12, 18, 18, 36, minus 18, 18, minus 12, minus 18, 12, minus 18, 18, 18, minus 18, 36, okay? And we're going to look at element B here, and we see that element B acts on nodes 2 and 3. And so this is going to be U2y, theta 2, U3y, theta 3. Okay. And then Kc is going to be the same thing. And so Kc, just for the sake of completeness, let me go ahead and write it all down again. Right. Oh, this is 1.67 E10. Right. Right. So we have 1.67 E10 times 12, 18, minus 12, 18, 18, 36, minus 18, 18, minus 12, minus 18, 12, minus 18, 18, 18, minus 18, 36. Okay. And this is multiplied by the degrees of freedom that node element C act on. And element C acts on nodes 3 and 4. And so it's going to be U3y, theta 3, U4y, theta 4. Okay. All right. And so that's, the element stiffness matrices for all of those. And for this problem, we also have a spring. And so the spring is going to be vertically here. So let me just kind of write down the spring just really quickly. Okay. And so this is going to be Kd. Okay. And so Kd here is going to be our spring constant K. Remind me again. So K is 175 meganewtons per meter. And so this is going to be 175 E6, right? 1 minus 1 minus 1, 1, right? So this is just simply our element stiffness matrix for a spring. And it's going to be multiplied by, the degrees of freedom that element D act on, which is U4y, U5y. Okay. All right. And so now that we've done that, now it's time for assembly. Okay. And so in assembly, remember we're basically putting all these element stiffness matrices into the global system. Okay. And so remember, for the midterm, I'm not, you've already kind of done a ton of calculations up to this point. And so, I don't want you to kind of write down a bunch of stuff again. All I want you to do is just to highlight in the global matrix, where you would insert, these guys. All right. And so in this global matrix, we actually have a 9 by 9 because we have 9 degrees of freedom. that we need to account for, right? And so let me draw 9 columns here. Okay, so first we have U1y, theta 1, U2y, theta 2, U3y, theta 3, U4y, theta 4, and also U5y. Okay. Okay. Let me make this a little bit neater. Okay. Right. And then of course this is going to be multiplied by those same degrees of freedom. So U1y, theta 1, U2y, theta 2, U3y, theta 3, U4y, theta 4, and U5y. Okay. And so from here, this is kind of like how we do, our, elements, global assembly, in the lectures, right? Because in the lectures, usually I don't have time to write everything down. And so you're going to have kind of the same time constraints in the exam. Okay. And so, all I want you to do here is just to basically just box or highlight, you can do that too. And so if you want to use a highlighter, that's fine. And box the regions where, you're going to insert the element stiffness matrices. Okay. All right. And so let's start with element A. Okay. So element A, I'm going to use this color. And so if you have access to different colors, either, on your writing app, on your iPad, or, just you have a colorful set of pens, that's great. And so you can use those. But, if you don't, then it's okay. So I'll show you what to do if you don't have, a colorful set of pens. Okay. Okay. And so if you have, element A, so element A here acts on nodes 1 and 2. And so 1 and 2 is going to be in this region up here, right? So it's going to cover all of the, degrees of freedom for, nodes 1 and 2. Okay? Right, so maybe that should go down a bit more, but it's okay. Okay. And then what you can do from here is you can just simply fill in the box just like that. Right. And so this tells me that where you would insert this element stiffness matrix into the into the global system without actually having to write it down. So I guess technically we should go a little bit below here. Okay. Right. And so that's just like that. Okay. Okay. And so if you have a different color pen, you can just go from here and say element B and insert there. But if you don't have a different color pen, what you can do is you can just write this entire system again, or you could use, a different marking scheme. Okay. And so let's say that we just have this kind of red pen right here. Okay. And then, and now we want to fill in the spot for element B. Okay. All right. And so element B, we know that it's going to be here, right? And so what it's going to do is going to encompass all the degrees of freedom for nodes 2 and 3. Okay. And so it's going to look like that. And then what you can do from here is you can use kind of a different pattern on the inside of the box. Okay. And so instead of slanted lines like that, what you can do is you can fill it in with like little circles or something. And so, if you do that, then I can clearly see that, you have two different, element stiffness matrices here, and they're going on different, different components. Okay. Okay. And so that's element B. And so now let's fill in element C. And so element C is, going to be, taking on nodes 3 and 4. Okay. So let's go ahead and put a box around elements 3 and 4. And so elements 3 and 4 are going to be all of that. And then same thing here, just use a different pattern to fill in the box. Okay. And so let's try checkerboard. Okay. And so with that, I can see that, that these are good. Okay. And then finally, what we have is the spring. Okay. And so the spring here acts on only U4Y and U5Y. And so for the spring, it's going to act on basically these these four, right? And so first we have U5Y, U5Y, which is going to be this one. Then we have U4Y, U5Y, which is here, right? Notice how I'm skipping over theta 4 because the spring doesn't act on, the spring doesn't support any rotation. And so, we're not going to have any theta 4 in there at all. Okay. And so that one's a little bit hard to see, but you can see that there's something in there, right? And so just like all the previous ones, we can use a different pattern here. And so I don't even know what's left. Let's use let's just kind of fill it in. Just fill it in completely, okay? Just so it kind of stands out on top of the checkerboard, right? And then of course, what you can do outside of here is you can kind of label what this is, right? And so you can say is that element A is going to be slanted, B is going to be bubbles, right? C here is going to be check marks or checkerboard, and element D here is going to be filled in completely. Okay, right? And so that's all I want you to do on the exam. And so you don't have to actually fill in the values, just mark it with the pattern, just that you let me know where you would actually insert it. Okay, and so that's the assembly step. And so that's the way that you would do it on the exam. And the last thing that I would want you to do is I would want you to apply the boundary conditions. So actually, let me change back to black. And then what I want you to do for this is to again, start from a blank, system of equations. Oops. So we have U1y, theta 1, U2y, theta 2, U3y, theta 3, U4y, theta 4, and U5y. And since we're doing boundary conditions, we're going to need our our forcing vector, and so make sure you include that. Okay. And then to apply the boundary conditions, I just want you to apply those. You can leave basically everything else blank. Right? And so let's go back to our original problem. And we can see here, we can see that here that we have a fixed support at node 1, we have a fixed support at node 5, and then we have a load of P that's acting on U4Y. Okay. And so let's go ahead and implement all of those into our matrix here. And so first, let me circle all the rows where we need to apply our fixed constraints. Okay. And so since we had a fixed support at node 1, that's going to knock out both U1y and theta 1. Okay. And then we also have a fixed support at U5y. Okay. And so from here, I just want you to fill in the rows for this boundary condition. Okay. Right. Right. And so that's what you would do for the fixed supports, right? And so remember, you would affect the fixed supports by changing the entire row to zeros and ones, okay? And you would and then change the diagonal entry to just 1, okay? And then also for the load is acting on node 4, right? Right. And so we're going to put that on the row for U4y. And then we're going to put the load in on the right-hand side. So do just exactly the same, but these are just the modifications that you would make just for the boundary conditions. Okay. All right. And so that's that's basically just a rundown of how you would do these kinds of problems on the exam, right? So remember, I don't want you spending time filling in this entire matrix and adding everything up. I just want you to tell me where those are, and then when I ask you for the boundary conditions, make just the modifications for the boundary conditions and leave everything else blank. Okay. All right. And so that's that's everything I wanted to say about beams. And so now let's move on to trusses. And I think, I have a feeling that, what people really want to see is 2D truss problems, right? And so let me go ahead and do that. Okay. All right. And so for 2D truss problems, our process is going to be exactly the same that we just went over. The only difference is in the element stiffness matrix. But first, let me just talk just generally, what truss elements are compared to beams. All right, and so beams that we just covered, we know that they experience transverse displacement and also rotations, and so truss elements will basically just support just compression and tension. Okay? And so in other words, one way that we can describe that is truss elements can only displace axially, or down the length of their other element. Okay. Right. And so visually, it looks something like this. And so here we have our truss element, which is, visually looks the same as our beams. But, the difference here is that, they can only displace in this direction, right? So you can either have, here we have tension, so that the truss element is kind of being pulled apart, or we can have compression, where they're given like that, okay? Right. And then just like in the beams, what causes these deformations here are going to be the nodal forces. And so here, we're just gonna have forces. We don't have any moments because there's no rotations here. All right, and so here we have our truss element, and let's say that we have a force here, okay, right? And we call those usually F1 and F2, okay? All right, so this is the 1D case, but I think 1D cases, I think most everyone has down pat pretty well. I think it's the 2D cases where things start to get a little bit complicated, right? And so for 2D cases, we have a truss element that's kind of arbitrarily oriented. Okay, we have something like that, and that at each of the nodes, we have both x and y displacements. Okay. All right. And so, here we're going to have, a displacement like this and displacement like this. And up here we have a displacement like this and a displacement like this. Okay. And so here we have u1x, this is going to be u1y, this is going to be u2x, and u2y, okay? Because in reality, what you have is displacement that goes, like this, down the length of the rod, just like we have in 1D. But since we like to work in traditional Cartesian coordinates, we break that slanted displacement up into its components, and so we have the x component and the y component. Okay. And then causing these displacements is going to be some forces, right? Okay, so let me draw the same element. Let me draw the nodal forces. Okay. Right. Right. And so for basically each displacement, we're going to have a nodal force that's associated with it, right? Okay. And so we list these as F1x, F1y, F2x, F2y. Okay. Right. And just like we saw with beams at the very beginning of this review session, what we're interested in is kind of the relationship in between these two, right? And so if you have kind of a general truss element or general truss equation, you're gonna apply some kind of external forces on that. And what we're interested in is, how is the structure going to respond to those forces? Okay. Okay. And just like we saw with beams, the way that we're going to see this is through an element stiffness matrix. Right? And so the element stiffness matrix for a truss, even though we covered it first, I think in a lot of ways is more annoying to do because we have lots of sines and cosines. So let me pull that up. Okay. And so the element stiffness matrix for a 2D truss is going to be 4x4 matrix, just like in the beams. Okay. And so out in front, we have the quantity 8e over L, which, of course, I'll define in a little bit. Okay. And then we have all of the sine and cosine terms, right? And so I think in the lecture, what I did was I just kind of wrote this as a symmetric matrix, but let me give you the explicit expression for, each of the 16 components, right? And so here we have cosine squared, then we have cosine sine, then we have minus cosine squared, and then minus cosine sine, okay? Right. And so since it's a symmetric matrix, I'm just going to write out that row into the first column, okay? Next, we have sine squared minus cosine sine minus sine squared, okay? Again, since it's a symmetric matrix, I can just take this row and kind of rotate it down. Okay. Then we have cosine squared, cosine sine. Okay. That goes there. And that's just like that. Okay. And so this here is the element stiffness matrix for a 2D truss, that you can use for finite element problems. Right? Okay, so there's a lot of quantities in here, so I need to define what all of these are. And so let me do that on the next page because I'm kind of out of room here. Okay. All right, and so some of these, so all of the quantities that we saw in that element stiffness matrix were the following. Okay, so we have A, and so A here is the cross-sectional area of the element. Okay. E here is the Young's modulus. Okay. L is the length of the element. Right. And so basically those are all the material properties and geometric properties of the element. Okay. In addition to this, we have C and S, right? And so C here is nothing more than cosine of theta, and sine here is sine of theta, which are cosine and sine of the angle. Right? So, every time that we have an element here in 2D, they form this angle theta here with the x-axis. Okay, and so C and S here are just going to be sine and cosine. Right? Okay, and so the other thing I want you to remember is the convention that we use to determine this angle. Right? And so remember the convention that we use is this angle is just not something that's between 0 and 90, and so you have to kind of really be careful with how you assign this angle. Okay, and so the way that we determine this angle is we draw an arrow from the lower numbered node to the higher numbered node. Okay. And so, just for the sake of example, let's say that, for this case, let's say this is node 1 and this is node 2. Okay. And so if we draw an arrow just like that, okay. And then once you do that, then, what the angle that you want to plug in is the angle that that arrow needs to rotate from the positive x-axis in order to get that to that position. And so determine theta by the amount that the arrow had to rotate to get to this position. Okay. And so in this particular case, I'll rotate to get this position from the positive x-axis. Okay. And so if we have the positive x-axis like this, okay, the actual angle that you plug in is not going to be, it's not going to be this one right here. Okay. And so the one that you plug in is going to be the angle that you rotate to get to here. Okay. All right. And so, with that in mind, you should be able to assign the correct angles for that. All right. And so that's just kind of review for, what we, for the 2D trusses. And so now let's do an example in the style of what, I would ask you to do on the exam. Okay. And so this is going to be problem 3B from homework 1, sorry. And so this problem looks like the following, right? And so we had a wall here. Okay. And then we had 3 elements. It's not to scale, so I think all of these are supposed to have the same cross-sectional area, but crappy drawing skills, right? Okay, and so this top element here is going to be element A, this middle one is going to be element B, and this bottom one is element C. Okay. And so this top node is going to be node 1, it's going to be node 2, to node 3, right? And this one where they all converge is going to be node 4, right? Okay. And then let's define their angles here. So let's see, this is 60 degrees, this is 45 degrees, and of course this last one is just 0. Okay. And then in terms of loads, we have 2 loads. Okay. And so both of those are going to have a load of P. Okay. All right. And so let's define the properties for this problem. Okay. And so the Young's modulus here is going to be 15 megapascal. The area for all of the elements is going to be 50 centimeters square. Okay. And the length of the elements are the following, right? So for the length of element A, what we have is 5 meters. The length of element B is 3 meters. And the length of element C is 1.5 meters. Okay. And I think the load here, P, is going to be 1 kilonewtons. Okay. All right, and so let's do this problem kind of in the same style as as in the midterm. Right? Okay, and so let's start with the element stiffness matrices. So let me kind of bring up this solutions here. Okay. And so the element stiffness matrices, we're just going to plug into our, equation, over there on the previous page. Okay. And so, for these 2D truss problems, what I usually like to do is I like to compute kind of everything ahead of time before I plug it in. Right? And so let's start with element A. Right? And so element A, first thing we're going to need to do is write out the angle for element A. Okay. And so, here it's tempting to use, 60 degrees here for the angle, but let's do the same test that we did on the previous page. And so let's draw an arrow from node 1 going to node 4 right here. Okay. And you can see here that, in order to get to this part, if we draw kind of the positive x-axis, this element here had to rotate by not 60 degrees, but 300 degrees. Okay. And so, we have that. And so with 300 degrees, we can compute cosine and sine. And so the cosine for this is going to be 1/2. And then the sign is going to be minus root 3 over 2. Okay. And then the last thing I'll compute here is the coefficient out in front. And so we have AE over L. Okay. And so A here, we have 50. We're going to convert this centimeter square to meter square. And so it's going to be 50 divided by 100 divided by 100. And so this is going to be 50 E minus 4 meters square. Okay. Times the Young's modulus. Young's modulus is 15 megapascal. And so there's 15 E to the 6 Pascal. Divided by L, where L here is 5 for element A. Okay, and so we punch all these guys into the calculator. Times 15E6 divided by 3. What we get is 25,000. Okay. Okay. So let me just kind of save some room here. And so this AE over L is going to be 25,000. Okay, and so with all that in mind, now we're ready to kind of plug this guy in. Okay? And so our element stiffness matrix is going to be AE over L, and so we're going to have 25,000 out in front. Okay? Times, all those, combinations of sines and cosines, right? And so let me go ahead and just fill this in, because we are running a little short on time, and I do have to run to another meeting in 20 minutes. Okay. So we have 1/4 minus root 3 over 4 minus 1/4 root 3 over 4, right? Minus root 3 over 4, 3/4 root 3 over 4 minus 3/4, okay? Minus 1/4 root 3 over 4, 1/4 minus root 3 over 4, okay. Root 3 over 4 minus 3/4 minus root 3 divided by 4 and 3/4. Okay. Right. And this is going to be acting on nodes 1 and 4. And so let's go ahead and put that, squeeze that in here, or not. Okay. And so, you can imagine that this is acting on U1x, U1y, U4x, and U4y. Okay. Should have pushed this to the left a little more. Okay. So actually, we kind of fill this in right here. U1x, U1y, U4x, U4y. Okay. And so that's what we have kind of on that right-hand side. Okay, and so that's element A. Okay. And so now let's do element B. And so before we kind of turn the page, let's determine the angle for element B. Right? Okay. And so just like we did for element A, we're going to draw an arrow here that goes from node 2 to node 4. And you can see in order to get here, we had to rotate a total of 315 degrees. Okay. Right. And so let's use that angle in for element B. Okay, so element B, theta is equal to 315. Okay. And so we do that. The cosine of 315 is going to be root 2 over 2. Sine is going to be minus root 2 over 2. Okay. And then AE over L, let's go ahead and compute that. And so this is 50 E minus 4. E here is, what was it? I forgot already. It's 15 megapascal, so 15 E6. Okay. And then L here, I believe, was 3. And so that's, oh, did I mess up? I think I messed up on the previous one. Okay, let me compute this first. So this is 50 E minus 4 times 15 E6 divided by 3. Okay, so I messed up the previous one because this is this right here is 25,000. Okay. And so what this one is over here, this one should be 15,000. So that was my bad. Okay. See, there's lots of places where you can make mistakes on these problems. Okay. And so let's write out the element stiffness matrix. Let me give myself a little bit more room here. Right. And so out in front, we're going to have 25,000. Then we're going to have 1/2, minus 1/2, minus 1/2, 1/2. Then we have minus 1/2, 1/2, 1/2, minus 1/2. Okay. Minus 1/2, 1/2, 1/2, minus 1/2. This is 1/2, minus 1/2, minus 1/2, 1/2. Okay. And this is acting on nodes 2 and 4. And so this is going to be U2x, U2y, U3x, oh, sorry, U4x, U4y. Okay. And so that's element B. And so finally, let's do element C. Right? And so element C, the angle here is pretty simple because we're just going to go from 3 to 4. And you can see that already aligns with the x-axis. Right? And so this theta here is just going to be 0 degrees. Okay. And so cosine of 0 is, of course, 1. And sine of 0 is 0. Right? And then let's do AE over L. And so AE over L is going to be 50 E minus 4 times 15 E6. Okay. And so that's 75,000 divided by the length. We divide by 1.5. And then what we get for this is 50,000. Okay. And so out in front, we have 50,000. Okay. And then, when we have, theta 0 here, we have, a pretty simple system because we have 1, 0, minus 1, 0. And then the column of all zeros, 0, 0, 0, 0. And then minus 1, 0, 1, 0, 0, 0, 0, 0. Okay. And then this is going to be U3x, U3y, U4x, U4y. All right. And so that's all the element stiffness matrices computed for this problem. Okay. Now let's move on to assembly. Okay. Okay. Remember, for assembly, I don't want you to actually fill these in, but just kind of show me where you would put these guys. Okay. All right. And so we have U1x, U1y, U2x, U2y. I'm just setting the columns for the matrix here. Okay. Right. And for the rows, we have U1x, U1y, U2x, U2y, U3x, U3y, U4x, U4y. Okay. And so just like we did before, let's go ahead and highlight the areas where we're going to do this. Okay. All right, so let's start with element A. So element A will do the patented slanted lines for this. Okay. And so element A here is going to be acting on nodes 1 and 4. Okay, so let's go ahead and draw boxes around that. Okay. And so first thing, we're going to have a box around the U1s. Okay. So that's the 1, 1 slot. Then we're going to go into the 1, 4 slot, and then the 4, 1 slot, okay. And then finally onto the 4, 4 slot. So let's kind of fill these in with slanted lines. Okay. And so that's where you would insert element A. So this one's going to get a little bit messy because we have so much converging on node 4, but we'll see. Okay. All right, and so element B, let's do bubbles. Okay, and so element B acts on nodes 2 and 4, and so we're going to have the 2, 2 block. There's going to be this one right here. Right? Then we have the 2-4 block. Then we have the 4-2 block. And of course, we have the 4-4 block, just like that. Okay. Let's go ahead and fill these in with bubbles. Kind of looks like a Lego from above. That's another way you can think of it. Okay. And so that's that, right? And then C, let's use checkerboard. Right? And so element C here is going to act on nodes 3 and 4. And so this is actually going to be one big continuous block here. Okay. And let's put the checkerboard in for this guy. All right. And so that's how you would, fill in this matrix without actually filling in its values. Okay. And so you can see here that, we have a big mess here at the U4 of U4X, U4Y block, because all of our elements there are converging on that node. Okay. And so, you're going to have a lot of overlap there. And so, if we were actually solving this problem, you would have to add a bunch of stuff into there. Okay. All right. And so that's the assembly. And so now let's do the boundary conditions. Okay. And so for this one, the boundary conditions it's going to knock out a bunch of this matrix. Okay. And so the boundary conditions, let's go back to our original diagram. Okay. You can see that we have pin constraints on nodes 1, 2, and 3. Okay. And so what that tells us is that, nodes 1, 2, and 3 just aren't moving at all. Okay. And so we're going to knock out basically all of those guys. Okay. Oh, actually, I'm sorry. So we have actually a roller support on node 3 right here. Right. And so that's going to affect our, what we do there. Okay. And so what we can see from the constraints is that U1x is equal to U1y, which is equal to 0. Okay. Same thing for node 2. Okay. And also U3x here is going to be equal to 0 as well. Okay. All right. So let's go ahead and apply our boundary conditions. So let me go ahead and draw the matrix again. Okay. So let me draw it something like this. Okay. It's going to be U1x, U1y, U2x, U2y, U3x, U3y, U4x, U4y. Okay. And since we're going to need the right-hand side vector, let me go ahead and put that in there. Okay. All right. So first, let's do all of the rows that have to do with the supports. Okay. And so that's going to be the U1x row, U1y row, U2x, U2y, U2y, and then U3x as well. Okay. And so for all of these lines, we're going to do the same thing. And so we're going to have change everything to zeros except for the diagonal term. 1, 2, 3, 4, 5, 6, 7, 8. Yep. Okay. And so it doesn't even have to be neat, and so you can be kind of messy like I am here. Right? So you can see I don't go all the way to the right. Okay. And of course, on the right-hand side here, we're going to have all zeros. Okay. And so that's the application of those boundary conditions. And then finally, we have our loads. Okay. And so our loads here, we have a load of P that's on the node 4. Right. So go back to our original diagram. We can see here that we have a positive load of P that's acting on node 4. Right. And so F4x is going to be P. And then we have a minus load of a load of minus P in the y direction. Right? And so this is going to be U4y is equal to minus P. Okay. And And so let's go ahead and put this into the matrix. And so P was 1 kilonewton. And so we're going to have a positive 1,000 here, and then a minus 1,000. Okay. All right. And so that's, that's another example of how you would do a truss problem in 2D. Okay. Okay. And so, hopefully this review was helpful, at least, if anything, just to demonstrate, how you would do these kinds of problems on the exam. Right. And so, I know that, we only covered 2 in this hour, 10 minutes here, but, I'm also talking over these things too. So, hopefully what I'm hoping for is, when you're doing this on the exam, it's you can do it in an efficient amount of time. But, it's still a decent amount of writing and a decent amount of computation. So definitely, definitely kind of manage your time wisely. All right, so best of luck with your studying, everyone. If you have any questions on this or anything that we covered, don't hesitate to send me an email. And then our exam is going to be next Thursday. Okay. All right, so here I'm signing off, and I'll see you in class.